Jairam ji ki, we will cover in this session chemical analysis of foods. When we say food, it has components like proteins, carbohydrates, fats, minerals, vitamins, and water. And of course, trace amount of various nutrients. It is a highly complex structure. It is very easy to define that it has protein, carbohydrate, mineral, vitamin, water, and fats. But it is very difficult to envisage how they all remain together. It's a very, very complex structure. And when we say it is complex structure, that means chemical analysis of foods is the most complex exercise for analytical chemists. We'll take one by one. We'll take first the proteins. What are proteins? Proteins are nothing but amino acids linked together. Each amino acid has two functional groups. So it's a very unique molecule, amino acid. On one end, that is normally conventionally when we write amino acid structure, right hand side, we always write carboxylic acid. And on the left hand side, we write the amino group. So carboxylic on the right side, amine group on the left side is amino acid. So each amino acid react with the other amino acid in such a manner that carboxylic acid group of one react with the amine group of another. That means the amino acid which whose carboxylic group has reacted will have amino free after the condensation, and the other amino acid whose amino group has reacted will have carboxylic acid as the free at the end of the day. Like this, all amino acids combine together through the peptide bond. The condensation of two amino acids forms a bond that is called peptide bond. So polypeptides and many polypeptides will make protein. So basically proteins are nitrogenous and all foods contain protein. Some will have maybe in traces like honey, and some will have large quantities like pulses. So protein is there in almost all foods. How do we analyze protein? There are two ways we can analyze protein. One is the direct method, where the protein molecule is directly evaluated, estimated. Indirect method, where protein directly is not evaluated, the protein constituent, that is nitrogen, is calculated, and from nitrogen we find out the amount of protein. Let us talk about the direct method. The first method in the direct is 4-mole titration. It is based on the principle that the amino acid group in presence of aldehyde, formaldehyde, will form a compound, a complex called methylene amino acid. It's an adduct methylene amino acid. So what is the unique feature of methylene amino acid? After reacting amino acid with formaldehyde, this group will have one carboxylic acid free, whereas the amino group is already bonded with methylene group. So amino acid and formaldehyde, after reaction, once they make this, the end product will have carboxylic acid free. That can be titrated with the base. So when we titrate with the base, the amino group converts to methylene amino, we have already said. Carboxylic acid remains unreacted, titrated with base. We find out the volume of the titer value of sodium hydroxide used. The formula is very simple. Protein percent is equal to how much sodium hydroxide is consumed. When we are titrating, how many milliliter of sodium hydroxide is consumed. What is the normality of sodium hydroxide multiplied by 9.04. This minus 0.14 factor, you will get nitrogen percent. Now let's see the other method, direct method, is spectroscopic method. In that, there are two methods possible. One is the biurate reaction and the other is the complexation reaction. In the biurate reaction, what we do is we take the solution which has copper 2 plus. Okay. So in copper 2 plus, in presence of alkali, the amino acids will reduce copper 2 plus to copper plus 1. Now copper plus 1 is colored. In the so that we can then by the color we can always by usual UV visible spectroscopy we can determine the content. In complexation, what happens is we use the reagent Folin Chiocalto. Folin Chiocalto reagent is nothing but phosphomolybdate and phosphotungstate. So a combination of phosphomolybdate and phosphotungstate makes an adduct, makes a complex with proteins. It's a blue-purple color. And by spectrophotometric method, we can determine at 750 maximum wavelength nm, we calculate the concentration of proteins directly. Now, there is a method called Lorry method, which is nothing but same based on Folin Chiocalto reagent. But this is basically for those proteins which are having phenol group, tyrosine and tryptophan. So there, this system is same. The pH is supposed to be in the basic 9 to 10.5, and once the color formed because of the complex, we estimate it by a spectrophotometric method. The indirect method, first and foremost, is we take the compound and digest it with sulfuric acid, strong sulfuric acid. Now, with strong sulfuric acid, what happens is all the nitrogen which is present in the protein gets converted to ammonium sulfate. Now, ammonium sulfate, we all know, in presence of alkali, will produce ammonia. So what we do is we take the sample, digest it with concentrated sulfuric acid. That ammonium sulfate which is formed, we will add sodium hydroxide. Immediately ammonia will be evolved. That ammonia which is evolved from the reaction, we will absorb in boric acid. So we will have formation of ammonium borate. That ammonium borate we can titrate with strong acid, and amount of acid consumed will tell us how much was ammonia, and how much ammonia will tell us how much nitrogen, and how much nitrogen will tell us how much protein. This is the basic concept. So the protein content that we find out will be, if we know the nitrogen, then 1.4 into volume of the acid consumed, the normality of the acid and weight of the sample. Then we will be able to find out nitrogen. The next step is, how do we know protein from nitrogen? So protein from nitrogen is we have the nitrogen content into a factor. That factor will be different from food to food. For example, in the case of dairy products, the factor will be 6.38. In the case of corn, it is 6.25. In the case of grains, it is 5.83. In the case of rice, it is 5.95. Wheat flour, it is 5.70. And in peanuts, it is 5.46. You would ask me on what basis the factor is determined. It is based on, we know how much protein is present. Say, for example, if protein present is 17% in the food, so 100 divided by 17 will give you close to about 6 factor. So generally, for all foods, we take this factor as 6.25. So I will again summarize and tell you, we took protein, added concentrated sulfuric acid, which will make the whole protein into ammonium sulfate. To ammonium sulfate, we added alkali. That produced ammonia. Ammonia we absorbed in boric acid, which will give us ammonium borate, which we titrated with strong acid. There is another method which was developed well before Geldal method, but was not tried that much, did not become popular that much as Geldal. The reason for that was because the principle of this method is little complicated. What do is we combust the whole food sample at 1000 degrees in presence of oxygen. Now what will happen is all the nitrogen which is there in protein will get converted into NOx, nitrogen oxide. Now that NOx we pass through copper, it will get reduced, and that nitrogen which is produced, we will inject into gas chromatograph and we find out how much is the nitrogen. The reason why this method was not popular is because it's not very easy to burn it at 1000 degree. Even if you are able to burn, to collect the nitrogen from NOx was the most complicated. But nowadays, we have equipment which all of this is possible. With the advancement of instrumentation, we are able to do it now in a very automated system, And that's why it is becoming more and more popular, because it gives precise results, it gives more accurate results. The next component after protein is oils and fats. Often, people, you must have seen, people are confused with whether it is oil or it is fat. I just want to tell you that oil and fats are chemically same. There is no difference. What are they? They are nothing but triglycerides or oligoglycerides. If not if some amount is present, di or mono, that is what is oligoglyceride. So oil and fats are all triglycerides. And what are triglycerides? They are the esters of glycerol and fatty acids. So glycerol has 3 hydroxyls. Each hydroxyl is esterified with the acid. So when all the 3 esterified, it is triglyceride. Only 2, it is di. Only 1, it is mono. Normally, naturally occurring oils and fats will have triglycerides. Very little amount is di and mono. And wherever there is di and mono, because of the photochemical reactions or by due to other natural conditions that are prevailing, there will be free acids as a result of that in the oil and fat, and that is not desirable. So basically, all are triglycerides, oil or fat. The difference is those products which are solids at room temperature, they are called fats, and those which are free flowing liquid at room temperature are oils. So whenever you listen people calling oil and fats, you must understand they are both same triglycerides. Now, why some are solid, why some are liquid is seen in this picture. You would see here one of the fatty acids which is there in this triglyceride has got 3 double bonds. One has 1 double bond. So if there are more and more double bonds in the structure in the alkyl chain of the fatty acid, then the product will be oil. More the unsaturation, more the liquefied form or oil, and less the unsaturation, it is fat. Basically, fats are completely saturated, like ghee, which is a mix of it, saturated but also has some unsaturated. So basically, we will be analyzing the fat. When we analyze the fat, please understand we say total fat. What do we mean by total fat? Total fat means anything in food products which is soluble in non-polar solvents. Something which is soluble in polar solvents like water, alcohols, is not fat. The fat is supposed to be which is soluble in non-polar materials. So basically, they are triglycerides, phospholipids, they are wax, or they are sterols or minor amount of non-fatty materials, which is oil soluble, which is non-polar soluble. To understand fat, we must understand the different types of fat. The first is total fat. What is total fat? You take your product, hydrolyze it. Why you hydrolyze it? To remove all that other than the fat, like proteins, carbohydrate, you remove. So hydrolyze it, and whatever is left behind, you extract. That will give you the total fat. Total fat means triglycerides as well as other compounds which are non-polar soluble. The free fat is you take the sample and you just extract. So you will get free fat. And if you take the sample, you extract, first you get free fat, then whatever is left behind you hydrolyze, and then you extract, that will give you crude fat. So we have total fat, free fat, and crude fat. And whatever free fat is there will be forming peroxide. So that is, we will discuss a little while later, the peroxide value of the food product. Now, direct solvent extraction will give you the fat content. So extraction in presence of alcohol, I told you, you just take food and just extract it, you will get free fat. Then you add non-polar, co-extract, so you will get fat which is non-polar solvent, and you get total fat there. Alkali hydrolysis method, that is Gottlieb method, Rose-Gottlieb method, where the hydrolysis is done by ammonia. I just told you, you hydrolyze it for the purpose of removing fat, which is combined in the structure of food, removing fat from protein and carbohydrate. So you hydrolyze it. So in the Rose-Gottlieb method, you hydrolyze it with ammonia. You take ammonia and you add alcohol, and at room temperature itself, ammonia dissolves all the protein. Alcohol will precipitate protein and will separate the oil from there. Then you add non-polar solvent and extract fat. So it is very simple. Alkali hydrolysis method, Rose-Gottlieb method. There is another method, that is solubilization extraction. This is for bound fat. I told you the fat which is entrapped in the structure, bound. So you dissolve the sample, and you don't dissolve the sample in just one hydrolysis. You do it in acid for hydrolysis to detach bound fat. So basically, we use hydrochloric acid, take the sample, put hydrochloric acid, and boil it for 30 minutes. So what that does is, it removes, it solubilizes, okay, all that is known fat. It removes the fat from the known fat. So bound fat is released. After that, you do the Soxhlet apparatus, and you do this solid liquid extraction, separate fat, weigh it, and find out this is the solubilization structure, find out the bound fat. What is free fat? As I told you, take the sample, just as extract. Whatever comes in the extraction with the solvent is your free fat. And we express the free fat as percentage or a milli equivalent per gram. We know that the oil and fats are triglycerides. That means all the fatty acid present there should be associated in ester form with glycerol. But it so happens that some of fatty acid remains free. How do we know how much fatty acid content, free fatty acid content is there in foods? For that, what you do is, you do simple extraction with diethyl ether or petroleum ether. They are non-polar solvents. So you collect fat in that, and whatever bound fat is present as free fatty acid in bound form, you do it by extraction with polar solvents like alcohol. So you collect the fat as such, which is free. Once you know the free fatty acid content, you will be able to measure the acid value of the oil and fat. And remember, acid value in free fatty acid is not desirable in oil and fats for food production. So acid value in free fatty acid is one and the same thing. For finding out how much acid value is present in the food, what do we do is, the free fatty acid which we collected, we titrate with potassium hydroxide. Okay? And after we titrate with potassium hydroxide, we find out how much is the volume of potassium hydroxide consumed for this. What is acid value? It is milligram of KOH required to neutralize 1 gram of free fatty acid. It is not desirable to have foods with high free fatty acid content. The virgin oil, for example, the plant oil like palm oil, like sunflower oil, mustard oil, the value of free fatty acid allowed is less than 4 milligram KOH per gram. In the case of non-virgin, it is 0.6. And how do we calculate the acid value? It is percentage of free fatty acid into 1.99. Now remember, the expression of free fatty acid is, either it is expressed as percentage of oleic acid by weight, or percentage of lauric acid by weight, or ricinoleic acid by weight, or palmitic acid by weight, depending on which oil we are doing it. So if it is as oleic acid by weight, then the formula is 28.2 into volume of the base required, normality of the base divided by W. For example, in coconut oil, we will do it as percentage of lauric acid by weight. So the formula would be 20 into volume of the potassium hydroxide or sodium hydroxide, its normality divided by weight of the sample. We are talking about the compounds, fat and oils. We must also talk about the volatile oil. There are volatile compounds, volatile oils, which we are supposed to know it. How do we do it? We do it by distillation. So we distill the volatile oil with boiling water, and we condense it in a tube in xylene and measure how much it is. That is the volatile content of oil and fats. One of the properties of oil and fats is melting point. We must remember that oil and fats do not have a sharp melting point. Why they do not have a sharp melting point? Because they are not pure compound. They are the mixture of various triglycerides, or monoglyceride be present also, or diglyceride also might be present. So the melting point actually is basically softening point. Also we call it slip point. How do we do this? We do this by taking the sample in capillary. First we melt the oil and fat. Once it is in liquid form, we make a small column in the capillary and then freeze it, cool it down so that it remains there as in the capillary. We put the capillary in water up to a specified depth, and then we raise the temperature. As we raise the temperature, the fat starts melting, softening, and it starts moving up. The temperature at which it starts that, and that is recorded, that is the softening point, slip point, or melting point of fats and oils. There is also a term solid liquid ratio. It is important for products like chocolates. Okay, for example, different chocolates, it is always recommended that you are supposed to keep it at a very low temperature in order to find out at what temperature it will flow, at what temperature it will remain solid. We do solid liquid ratio. This is done by normally in the dilatometer. You take your fat and start raising your temperature with 5-degree intervals. So you raise the temperature and you see how your fat and oil is expanding. Note down the change in volume, plot it with the temperature. So you will find the solid liquid ratio. The best way to do this, the best technique to do this is differential scanning calorimeter, in which the material is put in the pan of DSC, and you check the energy involved, because basically when this is happening, this is a phase transfer. So you find out, as I told you, solid liquid ratio is important for foods which are temperature sensitive. So which fat and oil is to be used for which kind of processed food will be based on solid liquid ratio. Differential scanning calorimeter is the best, but then NMR, the nuclear magnetic resonance spectroscopy, is the best ultimate technique. But I think the job would be done by the method that I just told you in the dilatometer. It serves the purpose in the food industry. We will talk about the Reichert-Messel RM value of fats and oils. Now, what is this actually? And why do we do this? This value actually helps us determine whether the desi ghee is adulterated or not adulterated. How do we do this? We actually try to find out how much is the high volatile component in this, which is water soluble. We all know that desi ghee has got unique triglyceride. Unique in the sense that the fatty acid which is there in triglyceride is butyric acid, caproic acid. That's why when we say cow ghee or buffalo ghee, you will see they smell very unique smell. That is because of butyric acid and caproic acid. They are highly volatile acids. So what we do is we take ghee, we take oil and fat, we saponify it. Once it is saponified, if it is butyric and caproic, it will dissolve in water. So, and it is high volatile, so it will saponify. This will get dissolved in water. We volatilize it and then condense it. So whatever that volatile component that came out will tell us about the value, the Reichert-Messel value of ghee. At the same time, in the same one, there is another term, that is Polanski value. This is contrary to Reichert-Messel value. Here what we do is we have water insoluble fat, which is highly volatile. In ghee, you have two kinds of highly volatile substances. One is butyric caproic acid, but then there is capric and lauric which is there in the coconut oil. So if there is an adulteration in ghee of, say for example, these cheap oils like coconut oil, you will be able to find it by Polanski value. Polanski value is nothing but we take ghee, we saponify. After saponification, what happens is we add water. So whatever fatty acid which is water soluble, we have already seen Reichert-Messel. We have removed it by distilling. Whatever is insoluble remains behind. So basically, Polanski value is opposite to Reichert-Messel value. This is volatile component but water insoluble. What is rancidity? When the food based on oil and fat is left for longer, what happens is oxidation takes place. The food products, as we already know, that there are double bonds in the oil and fats, they will get oxidized. There will be a formation of peroxide. That peroxide will oxidize the double bond, and it will give a smell, a bad odor or a different odor which is not desirable. That we do it by rancidity. By rancidity, we can make out whether the food is going to be spoiled or not, whether it is okay or not. How do we do this? We do it by the Chris test. We take the sample, we add chloroglucinol as a reagent in ether in the presence of hydrochloric acid. If there is a reddish color, it means it shows the presence of epihydrin LDI, and that shows that rancidity is there in the sample. How much rancidity is there? Depending on the intensity of the color, we can do it by spectrophotometer at 540 nanometer as the maximum wavelength. So rancidity and peroxide value, they are almost the same. How do we do the peroxide value? They indicate the same, but rancidity tells you well before the peroxide formation takes place, but it is one of the parameters for food products quality. So how do we do the peroxide value? And the peroxide value, as we know, is the indicator of oxidative rancidity in fats. Okay, it is also the peroxide content in fats. It can detect rancidity. It is nothing but milli-equivalent of peroxide oxygen per kg of the material. How much milli-equivalents of peroxide present in the food per kg of the food is peroxide value. So when we treat the sample with acetic acid chloroform medium and we add Ki in it. So because peroxide is there, potassium iodide will liberate the iodine. We titrate the iodine with sodium thiosulfate and we calculate the peroxide value by normality of thiosulfate into volume of titer value. That is, we titrated the iodine with, that is the normal titer value of sodium thiosulfate into 1000. I repeat, peroxide value is nothing but normality of thiosulfate, amount of thiosulfate consumed into 1000 divided by weight of the sample. Now, next parameter of oils and fats is saponification value. What is saponification? Saponification is nothing. The oil and fats, they hydrolyze. They hydrolyze in presence of alkali. So, when they get hydrolyzed, what do we get? We get glycerol and we get fatty acids separately. And that is the saponification. So, by knowing the sap value, we can determine what type of oil and fat is there. How do we do this? And this is actually nothing but milligram KOH required to saponify 1 gram of oil or fat. How do we do this? We reflux the oil or ghee with a non-excess of alcohol alkali. So when we reflux oil or fat with KOH, that means we are saponifying. It is saponified. Once it is saponified, it forms the glycerol and fatty acid. The total alkali the alkali can be used to find out how much fatty acid is produced. If we know how much fatty acid is produced, we can back calculate how much was the sap value of oil and fat. So we titrate the fatty acid produced along with glycerol with either caustic, sodium hydroxide or potassium hydroxide, and we determine how much is the sap value. Once saponification value is indirectly proportional to molecular weight of fatty acid in fat. So if we know the sap value, we can calculate what is the molecular weight of oil. For example, palm oil, it is 195, coconut oil 258. These are the sap value. Palm oil is 195. So by this formula, 56.1 into 1000 into 3 divided by sap value minus acid value will give you the molecular weight of palm oil. Olive oil, the sap value is 135, coconut oil 258, palm oil 195. When I say 195 sap value, that means it needs 195 milligram of NaOH for 1 gram of palm oil. Or if it is sap value 135, it needs 135 milligram of sodium hydroxide for 1 gram of olive oil. Sodium hydroxide or potassium hydroxide. If it is potassium hydroxide, it is 56.1. If it is sodium hydroxide, then it will be the equivalent weight of sodium hydroxide there instead of 56.1. Unsaponifiable matter. What is unsaponifiable? The matter which we are not able to saponify in oil and fats. We have seen that all fatty matter dissolves in non-polar solvents. The ones which are saponifiable are the oil and fats of triglyceride type, but the others, non-triglyceride sites, are the non-saponifiable matter. So we saponify the matter, and whatever is remaining behind, we know it as unsaponifiable matter. This gives us a parameter to find out the quality of oil and fats. Then there is a term called acetyl value or hydroxyl value. This is nothing but acetylation. If there are free hydroxyls in oil and fats, they will react with acetyl value. They'll react with acetic anhydride. How much anhydride is consumed will tell us how much hydroxyl value is there, and this will tell us how much free alcoholic group is there. We have talked about the fatty acids, fats and oils having the unsaturation. The unsaturation is done by iodine value. Iodine value is nothing but, because we know each double bond will consume one iodine molecule. So iodine value is nothing but iodine in milligram absorbed by 100 gram of oil and fat. How much iodine is consumed will tell us how much is the unsaturation in this. It will vary from type of oil and the unsaturation level of oil. For example, in ghee, the unsaturation is almost about 35%, and the iodine value of ghee is 34. How do we determine the iodine value? We take the sample in carbon tetrachloride, add excess of which solution? Which solution is nothing but iodine monochloride in glacial acetic acid. Then we add potassium iodide, and the iodine liberated we titrate with sodium thiosulfate. So the iodine value will be nothing but the titer volume of sodium thiosulfate. The normality of sodium thiosulfate, 12 into 12.69 divided by weight, will be the iodine value. These are the values of iodine value. For example, ghee 34.5, groundnut 43.2. This is an experiment where adulteration of ghee is done with groundnut oil, coconut oil, or animal body fat. And this is done at 10%, 5%, and 10% level. Look at ghee when it is adulterated with groundnut oil, 10%, the iodine value increased to 43.2. So if ghee is mixed with groundnut oil, the iodine value will be reflecting it. But suppose ghee is mixed with animal body fat, it hardly matters because their iodine value is matching. The sap value is also matching. So it's really difficult to determine. If somebody is mixing animal body fat in ghee, it is very difficult to find out from these methods iodine value or Polensky or Reichert-Massel method. Iodine value of various oils oils is there. Coconut oil is 7.5 to 10.5, olive oil 79 to 90. You can imagine olive oil, so much of unsaturated. Sunflower oil is 125 to 140 milligram per 100 gram of fat. And look at mustard oil, 98. The ghee is 26 to 38. Now talk about carbohydrates. Carbohydrates are of two types, simple and complex. Those which are simple are monoglyceride or diglyceride, and the complex are starch, glycogen, and fiber. Now remember, monosaccharides are molecules with carbon 6 carbon. The disaccharides is two monosaccharides joined together. So the carbohydrate, we'll discuss first the fiber. We'll talk about total dietary fiber. We take the sample, we remove fat. We know the method how do we remove fat by hydrolyzing it. So we gelatinize with heat stable alpha amylase and to hydrolyze starch. We gelatinize it with that starch. For protein, we gelatinize with protease, and for dextrins, we gelatinize with amyloglucosidase. So we take the sample, we add alpha amylase, protease, and amyloglucosidase. So all these three will be hydrolyzed. We add to this ethyl alcohol. Once this is hydrolyzed, it will precipitate the soluble dietary fiber. We filter it, wash the residue. After washing the residue, we analyze protein and also ash. The total dietary fiber will be nothing but insoluble dietary fiber and soluble dietary fiber. I will repeat. Soluble dietary fiber is the one which is dissolved by the protease, amylase, and amyloglucosidase. Just like in our body, the enzymes will digest this. Whatever is digested by them is soluble. Whatever is remaining is insoluble. And combined together is total dietary fiber. See this, I just told you, soluble dietary fiber is by putting these enzymes, hydrolyze them. So weight of the residue minus weight of protein and ash, after all that is solubilization is done, is soluble dietary fiber. Crude fiber and dietary fiber is that after having done gelatinization with all the enzymes, and after all treatments, whatever fiber is remaining is your crude fiber. Let's see. We take macro constituents of food, including remnants, edible plant, cells, polysaccharides, etc., oligosaccharides, wax, cutin. So we take dietary fiber is separated by constituents like enzymatic hydrolysis. Crude fiber is separated by acid and alkali. The difference is crude fiber will not be digested by enzymes, will only be digested by the acid and alkali. How do we differentiate it? We take the food, we digest it with sulfuric acid. So once we digest with sulfuric acid, some of the crude fiber will be removed. The digestion of the food is done with sulfuric acid, followed by digestion with caustic. We collect the residue, and that residue we dry. We ignite it in the muffle furnace, and the weight of the residue we calculate from this. The crude fiber is nothing but the percentage mass W1 minus W2 divided by W. We took the sample. W1 is the dry residue weight, W2 is the ignited residue weight. That tells us how much is the crude fiber. Now let's talk about ash. Ash is nothing but when we burn our food, whatever is remaining behind is the total ash. So we incinerate food, all organic matter will be burnt, all inorganic matter will be left behind. Now inorganic matter can be nutrient, can be adulterant. Now we do several ways of doing the ash analysis depending on the food. The first and foremost is the dry ash. How do we do dry ash? We take the food as such and we burn it at 550 degree and 600 degrees. Whatever remaining behind is dry ash. What is wet ash? We take the food in acid and then filter it. So whatever acid soluble is there will go away, and acid insoluble we burn it and find out the wet ash. Now whatever acid soluble is there, we calculate it for elemental analysis. So to find out how much nutrient is there. What is sulfated ash? When we burn the material dry, some of the metal ions, some of the metal atoms, they get evaporated. For example, lead. Lead is a toxic metal. In food products, it's very dangerous lead residue. So for those kind of foods, especially herbs and spices, the regulators insist that we do sulfated ash. How do we do sulfated ash? We take food, put it in sulfuric acid, treat it with sulfuric acid. All the ash will be converted as sulfated ash. You burn it and find out how much is ash. That is your sulfated ash. Acid insoluble ash is nothing but like wet ash. When we were doing wet ash, put the food in acids. Whatever is dissolved in acid, separate it. Remaining residue is acid insoluble ash. Now let's talk about the sugars. There are two types of sugars, reducing sugar and non-reducing sugar. As you see it in this structure, there are 6 carbon atoms and there are 5 hydroxyls, and at the end of the day on the 6th one there is aldehyde group. Aldehyde groups have a capacity to actually reduce Fehling solution, which is copper sulfate. So Fehling solution is, if it is reduced, it will give a color. So to find out how much reducing sugar and how much non-reducing sugar, this is the test. The method is Lane and Anon test. And how do we do this? What basically we do is we take the sample, we take methylene blue as the indicator and add this Fehling solution. The color is there, and that color we determine spectrophotometrically. Now remember, all monosaccharides are reducing sugar. Why they are reducing sugar? Because they have aldehyde group free. But when one monosaccharide attaches with another monosaccharide and makes disaccharide, then it forms two types of sugar. One reducing sugar, the other one is non-reducing sugar. Now let us take, for example, lactose. Lactose is a reducing sugar. For example, in lactose, we have galactose and glucose. You have the aldehyde free there. So this is one sugar, it is reducing sugar. But there are 4 or 5 sugars which are non-reducing sugar. Why they are non-reducing? You see the structure of glucopyranose. Here on the first carbon, there is hydroxyl on the anoramic carbon in the lower plane, and the aldehyde on the upper side is available for reduction. The non-reducing sugars are sucrose, trehalose, raffinose, stachyose, verbascose. These non-reducing sugar don't have a free aldehyde group. Say for example maltose. Maltose is a reducing sugar because the aldehyde group is there. There the disaccharide chain opens up when we put it along with the reagent. In the case of non-reducing, it does not open up. It remains intact. Let us see how do we determine the reducing and non-reducing sugar. We take the food sample. First, we clarify the sample by clarifying agent like lead acetate and lead oxalate. Filter it, we get the filtrate. In the filtrate, we add phenol solution and concentrated sulfuric acid. We get the color, and that color we measure by UV spectrophotometer at 490 nanometer to find out how much is the strength. So that will give you the reducing sugar. You see the structure of sucrose, which is non-reducing sugar, because that aldehyde group is not available for reduction. And this aldehyde group is in such a manner that the chain is not able to open. Whereas in the case of reducing sugars, it opens easily. The next carbohydrate is starch. In the case of starch, it is acid hydrolyzed or enzymatic hydrolyzed. Okay. So what we do is we leach out sugar by precipitating starch with alcohol. So we add alcohol to the sample, the starch will be precipitated, and to that we add hydrochloric acid. Okay. Resulting reducing sugar is, the whole thing will be converted into reducing sugar. We know very well reducing sugar, how to do it. We have just done it spectrophotometrically. We'll repeat that. So we take sample, we precipitate the starch by adding alcohol. That starch, we convert that into reducing sugar, and whatever that reducing sugar is there, percentage reducing sugar, multiplied by 0.90, and we get percentage of starch. The enzymatic hydrolysis method, instead of HCl, involves we take the sugar with alcohol, leach out sugar with alcohol. That means the starch will be separated. If there is a fat, we remove the fat, and then we take KOH and wash it with 80% ethanol. The starch which is collected is then gelatinized with amyloglucosidase at pH 4.5. That converts the starch into glucose. So basic idea of doing starch content is we convert all the carbohydrate that is starch into reducing sugar. And reducing sugar, we do it by the method that we have just talked about. So from this, what did we learn? We learn what is protein, how do we determine protein, what are the direct and indirect methods of doing protein. We talked about Geldal method, we talked about Dumas method, we talked about biurate, and we talked about the method where Chiocalto reagent, Follin Chiocalto reagent, where we have this color and do it spectrophotometrically or titrimetrically. We differentiate water content, water activity in food, differentiate crude fiber from dietary fiber. Something which is not digested by enzymes, okay, in the body is the crude fiber. Something which is digested by the enzymes is dietary fiber. Dietary fiber can be soluble, can be insoluble. So what is the significance of ash content? We have seen different type of ash. How do we do it? We do it dry ash, we do it wet ash, we do it sulfated ash. Why do we do all of them? We have learned it. We also have learned how what is methylene blue indicator in determination of sugar, because it's very, very sensitive. So for the failing solution, when we use, this is the best indicator for that. What are the physical parameters used for quality evaluation of oil and fats? There are several. The melting point, softening point, unsaturation level by iodine value. We do it. Uh, we do it. Uh, Polanski method for checking the water insoluble high volatile compound. We do it Reichert-Massel method, the RM value of oil and fat, which will give us water soluble, highly volatile, water soluble like butyric and caproic. Define the iodine value. We have already talked about each double bond will absorb one molecule of iodine. So that is one which tells us about unsaturation. So we have talked about which method. We have talked about how do we do RM value, rancidity we have talked about, because by hydrogen peroxide, the double bond gets oxidized and leaves the rancidity, which is related to peroxide value. So all that is discussed. Thank you very much. I hope you understand it.